This will be an overview of Target Compiler Technologies located in Leuven, Belgium. We'll be discussing the IP Designer tool suite, why use an ASIP, an application-specific instruction set processor, and get into some programming examples. Founded in 1996, Target Compiler Technologies is one of the pioneers and a leading supplier of configurable processor technology. Headquartered in Leuven, Belgium, and with U.S. headquarters in Boulder, Colorado, Target produces EDA tools for the design, programming, and verification of application-specific processors, an ASIP. ASIPs are key building blocks for both single-core and multi-core system-on-chips. Whether software developers like it or not, and whether they're prepared or not, virtually every semiconductor maker worth their salt is producing multi-core system-on-chips. These SoCs typically pair 2 or more CPU cores with additional application-specific hardware accelerators to provide a complete system. In recent years, application-specific instruction set processors, ASIPs, have become popular because they simultaneously offer high performance, low power, and short design cycles. In contrast to off-the-shelf processor cores, ASIPs include dedicated functional units and machine instructions that speed up execution in a given application. So we've talked a little bit about additional hardware units and functional accelerators, but now let's look at the compiler. How important is the compiler? Any first-year programmer knows that the choice of a compiler makes a big difference to the quality and speed of your code. Some benchmarks, like Nullstone, are actually tests of the compiler, not the hardware. For instance, we've got one example of an NXP LPC 2939 chip that delivers 0.54 core mark per megahertz, and another example of the same chip that gets 1.18. That's a 2-to-1 difference on the exact same device. The only difference between them, the compiler. Apple develops their own SoCs and serves as the best example of a growing trend of companies leveraging their own designs. Using a TI C55X DSP and comparing Target's compiler cycles and code size to TI's compiler, the cycles and code size, you can see on the right the gain and code size of the Target compiler versus TI's. The green number shows Target's compiler bettered TI's compiler by that certain percentage. This is just another example of what was referenced before. The compiler does make a difference. Target's EDA tools allow you to develop a specialized processor called an ASIP, an application-specific instruction set processor, and a unique instruction set that works in conjunction with this processor. This ASIP and its instruction set are tuned to your C algorithms, resulting in the highest speed, lowest power, configurable processor available, period. Once the processor has been defined by our processor modeling language called NML, you run your C algorithms and receive a histogram output showing clock cycles per functional block in your processor. It's then simple to see which blocks in your processor are bottlenecks to throughput. You make a change using NML and run the process again to see if you have lowered the cycle count on the specific blocks, thus increasing your throughput. The end result is an ASIP, a specialized processor that is tuned to your application and is designed by default for the lowest power and highest speed given your C code. You can think of it like this. If we look at efficiency along the x-axis and flexibility along the y-axis, A general-purpose microprocessor is very flexible. It can be used in almost any application. In contrast to the microprocessor, you have a hardwired data path, a fixed function RTL. It's very efficient, low power, but not flexible. You can't reprogram it should you make a mistake, and it takes a lot of time to develop. ASIPs, the application-specific instruction set processor, bridge the gap between the general-purpose microprocessor and the hardwired RTL. ASIPs are programmable and with their custom instruction set are tuned to your application. So why design with an ASIP? You can maximize your performance, you can minimize power dissipation, and you can leverage the benefits of programmability. We'll now look at some of the IP Designer tool names. Chess is a C compiler. Bridge is the linker. Darts is the assembler. Checkers is the instruction set simulator. And Go is the RTL generator. In the IP Designer tool suite, you'll see a processor model block. Target uses a language called NML to model the processor, basically giving you a structural skeleton of what the processor looks like. This also provides customized instruction sets for the processor model. This is also the area where you can create customized opcodes for your specialized processor. The next block has to do with your C algorithms and software development. You can see the C compiler, the assembler and linker, binary files, the debugger and profiler, which gives you the histogram, and the instruction set simulator. Running this loop allows you to tune the processor to your C code, as you'll see in a few minutes. And finally, the ASIP synthesis, the RTL generator, synthesizable RTL, RTL simulator, RTL synthesizer, leading down to your ASIC or FPGA. So putting this all together, we'll do an example of motion estimation, sum of absolute differences. The sum of absolute differences is an algorithm for measuring the similarity between image blocks. It works by taking the absolute difference between each pixel in the original block and the corresponding pixel in the block being used for comparison. These differences are summed to show a simple metric of block similarity, showing the difference between the two image blocks. This example uses the sum of absolute differences to identify which part of a search image is most similar to the template image. In this example, the template image is 3 by 3 pixels in size, while the search image is 3 by 5 pixels in size. Each pixel is represented by a single integer from 0 to 9. There are exactly 3 unique locations within the search image where the template may fit: the left side of the image, the center of the image, and the right side of the image. To calculate the SAD values, the absolute value of the difference between each corresponding pair of pixels is used. The difference between 2 and 2 is 0, 4 and 1 is 3, 7 and 8 is 1, and so forth. Calculating the SAD values for each of the locations is shown on the right. For each of these 3 image patches, the absolute difference are added together, giving the SAD values of 20, 25, and 17 respectively. From these SAD values, it is apparent that the right side of the search image is most similar to the template image because it has the least difference as compared to the other locations. Here is shown the C code for the sum of the absolute differences equation you saw earlier. We will now start developing a specialized processor to execute the C code. Here is shown our initial design to run our C code. We're going to use a single port memory, an address generation unit, an 8-bit register, an arithmetic logic unit, shift register, and a multiply accumulate. Also, you see the bus structure that was created through NML. Here are the results of running our C code through our specialized processor. You can see the total cycles of 87,724, and all the way to the right, the number of gates, 13,053. Here we see the profile table generated by the instruction set simulator, showing a histogram and which code is taking the most clock cycles. What we do now is analyze the code and see if there's any blocks or functions we can add or combine within the processor to increase speed. In Design 2, we've decided to add another address generation unit, allowing us to read and write from the register ports at the same time. We've also created a special block called an add difference plus add on the very right side, and we've made the memory now a dual port memory. We've configured this in NML and we'll run it again. Looking at the results of Design 2, our total clock cycles have went down to 14,000 clocks. That's an 84% decrease in clock cycles needed, and the gates have only gone up by about 9%. We're on the right track here to improving our design. By reviewing the histogram again of Design 2, we see there's an area of code that is still using way too many clock cycles. We're going to make some hardware changes and run this again. In the interest of time, we've added another data memory port. We've gone to vector accelerator, a SIMD architecture, and you can see that the total cycles have gone down to 5,906, and the gate count has just about doubled to 29,000. In Design 6, we've added some vector registers in hardware. We've made a vector add and a vector subtract. We've added ILP, instruction level parallelism. You can see in the green code there. And we've gone down from 72,000 total cycles in Design 1 to 1,791 total cycles. So in summary, Target Tools helps you develop and accelerate ASIP design. You have true architectural freedom and exploration. You have patented graph-based C compilation technology, automatic hardware generation, extensive verification, and it's a proven technology used by many customers. I hope this brief video has helped you better understand Target Compiler technologies. You can see us on the web at www.retarget.com, or please feel free to give us a call in Leuven, Belgium, or Boulder, Colorado. Thank you for watching.